Hi there! In this video, we're going to do a second example problem of a series of 3 example problems dealing with energy and energy conservation. And so in this problem, we have a spring of stiffness 560,000 joules per square meter. That spring is compressed 0.850 meters to launch a 1,000 kilogram roller coaster cart as shown in moment A in the figure. At the top of the loop, which is moment B, the cart has a speed of 14.3 meters per second. The track is smooth enough to be considered frictionless. I've highlighted 560,000 joules per square meter because if you're one of my students following along with the handout that I gave you, there's a typo in the handout that says 56,000 joules per square meter for that spring stiffness. But in order for this problem to actually physically work, it needs to be at least 560,000 joules per, or it needs to be bigger than 56,000. So I made it 560,000 joules per square meter. So fix that typo in your packet, please. With that, let's get started. Part A asks us to annotate the sketch with a 0 reference level for gravitational energy and the other given information in the problem. So I'm going to go ahead and do that right now. And there we have it. I have drawn in a 0 reference level for height at the lowest point of where the cart is, annotated with the cart's mass, the stiffness of the spring, how much the spring gets distorted, the speed at moment B, and the height at B, which is the thing that we're going to want to find in this problem. Part B asks us what is the vertical height of the loop, and asks us to start by modeling the situation with an energy bar graph. Here's an energy bar graph. Let's go ahead and use that to model the situation. We'll start by defining a useful system. I think I might want to put the cart, the gravitational field, the spring in the system, and I put the track in parentheses here. The track isn't an energy giver or receiver if there is no friction, and so we don't need it. And it's fine to leave it off, probably better to leave it off, honestly. But it's okay if you leave it on. And now, energy at moment A here. Let's go ahead and think about what energy is relevant at moment A. We have a compressed spring with a lot of elastic potential energy, but that's it. There is no chemical energy. There is no height above the 0 reference level because we put the 0 reference level at where the cart is at moment A. The cart's not moving at moment A, so there's no kinetic energy. And thermal energy, we always set to 0 at our first moment by convention. And then let's look at the energy at moment B. I modeled it as something like this. There's a split between gravitational energy because we're higher than our 0 reference level, and kinetic energy because the cart is moving. No chemical energy, the spring is no longer compressed, so there's no more elastic energy, and it's a smooth, frictionless roller coaster, and so there's no thermal energy. How did I know to split the energy evenly between gravitational and kinetic? I didn't. I made a guess. If you did 3 and 1, or 1 and 3, that works as well. Writing this out as an equation, this looks like the elastic potential energy at A must be equal in amount to the gravitational potential energy at B and the kinetic energy at B. So now we've used the energy bar graph to model the situation. Let's use this equation to answer the question. So I like to, as always, write down a list of what information I've been given and what information I'm trying to find. So let's start with the given information. I know that the spring constant, that stiffness of the spring is 560,000 joules per square meter. I know that the spring is distorted. Its length has changed by compressing it 0.850 meters. I know that the speed at moment B is 14.3 meters per second, and it's not explicitly stated in the problem, but most roller coasters I'm aware of are on Earth, and so the gravitational field strength that's relevant for this problem is 9.81 joules per meter kilogram. And let's find, or we're trying to find, we want to know the vertical height. The height at moment B is our unknown. So now I have a nice organized way to list of things to refer back to. It's just way easier if you do that. So got to give us and finds. Let's go ahead now and solve the problem. The sort of cream colored background is where I'll be doing my work, and the blue box says which step of the problem solving method I am on. So let's get started. I'm going to start by restating the energy conservation equation that the elastic potential energy at moment A is equal to the sum of the gravitational potential energy at B and the kinetic energy at B. And each of these has a nice handy mathematical model that we developed in the lab. Elastic energy can be modeled as 1/2 the stiffness K times the distortion of the spring delta L. And I put a subscript A there because we're talking about the subscripts or the spring's distortion at moment A. And that's, it's 1/2 K times delta L squared. And then gravitational energy can be modeled as mass times gravitational field strength times height. And I've annotated that height with the subscript B to indicate that we're talking about the height at moment B. And the kinetic energy can be modeled as 1/2 the mass times the speed at b squared. You'll notice I'm keeping some color coding going. The elastic stuff is orange, the gravitational energy stuff is purple, the kinetic energy stuff is blue. Cool. I'm trying to isolate my find. Before I even start thinking about doing that more, though, I really hate when I have fractions of 1/2. If I cannot deal with fractions, I'm going to avoid it. So I'm going to start by multiplying 1, 2, 3 terms by 2. And so it's 2 times the stuff in orange equals 2 times the stuff in purple times 2 times the stuff in blue. If I carry out that multiplication, I end up with 2 times 1/2 KL squared, delta L squared, is a whole K delta L squared. 2 times MGH is 2 MGH. And 2 times 1/2 MV squared is a whole MV squared. Reminder, this 2 does not distribute because we're multiplying these things together, not adding them. So this is all one term being multiplied by 2. Cool. And now what is my find? My find is the height. I'm going to highly recommend when you have 1, 2, 3 terms you're dealing with, we have an orange, a purple, and a blue term here, a 2-step process. Step 1, get the term with the find by itself. So that's the purple term here, get it by itself. And then 2, use division to get the actual find by itself. So we're going to start by getting the purple stuff by itself. And the way to do that is to subtract off the blue stuff. We're adding the blue stuff right now, subtract it off, and then we'll have just the purple stuff by itself. So step 1, isolate the group of variables. That's all one term with the thing you're trying to find. So if we subtract off mv squared from both sides of the equal sign, plus mv squared minus mv squared, these will add to 0, and we're left with just minus mv squared on the other side of the equal sign. Something like that. K times the distortion squared minus mass times speed squared equals 2 times the mass times the gravitational field strength times the height at B. And now I've isolated the purple group of variables that has my find. And so that was step 1. Step 2 now is to divide each side by everything else to get the find by itself. So everything else being 2mg here, the stuff that's in front of the h, divide by 2mg on both sides of the equal sign, and we're good to go. If I do that, everything on the left here divides to 1 except, everything on the right divides to 1 except for h. And here I'm left with this expression on the left. The mass on bottom does not cancel with the mass here because this m is dividing both of these terms, the blue and the orange, and there's no mass in the orange term. And so we can't do any canceling or dividing of the masses here because it would have to be here, and mass would have to be in this term and this term to do that. So we're not going to divide the mass on the left side of the equal sign, just on the right. But now I pause, I reflect, I say, yay, I did it. The thing I'm trying to find, h, is by itself on one side of the equal sign. I look at the other side of the equal sign, and it's a kind of messy algebra expression, but k, delta L at moment A, m, v at moment B, and g are all in my givens list. So ta-da, I did it. I found the thing I'm trying to find based on the things that are in my givens list. Now that I have done that, and only now that I have done that, it's time to plug in numbers. So that's step 3 here. We're going to plug in some numbers. Those numbers are all coming from this list here. And I'm going to grab my handy dandy calculator. And plug in, this is from the Desmos graphing calculator. I highly encourage you to get a calculator, like a graphing calculator, that allows you to type out the expression just as you wrote it. But if you are using a more simple calculator, make sure that you know the order of operations and do that appropriately. And overall, I'm seeing 10.1992864, but every number here has 3 significant figures, or it's exact, so I'm going to round my answer to 3 significant figures and say that the height at moment B is 10.2 meters. and put a box around it and say, there we go, I'm done. The only thing that's preventing me from calling it a day here is, does this expression really give me something with units of meters in the end? Let's do a unit check to make sure. Whew, it's going to be a messy one. Stick with me. The units for the orange, here's all of them. The orange expression has joules per meter squared times meters squared. So that's this term here. The blue stuff has kilograms times meters per second. That gets squared. So that's kilograms times meters per second quantity squared. The denominator has a unitless 2 multiplied by kilograms multiplied by a joules over meters times kilograms. So that's this stuff down here. Let's take that apart one at a time. I'm noticing first that those meters squared canceled. The next thing I'm noticing is that group of stuff is our definition for a joule. A kilogram times a meter per second quantity squared is what a joule is defined to be. So that's just a joule. I'm also noticing in the denominator there, we have some kilograms that divide to 1. So this does already simplify down to a numerator of joules minus joules and a denominator of joules per meter. Let's make sure we know where each of those comes from. The joules in the top right comes from that expression. The joules in the top left come from that joules there. And the joules per meter in the denominator come from right there. Now, some of you might see that and think joules minus joules, well, that's 0. Except we're just checking units here. We're not checking number values. And so it's more like if I have 7 apples minus 3 apples, I get 4 apples left over. So I can subtract apples and get apples. Here, if I subtract something with joules with something else with joules, I'm going to get something with joules in the end. So that numerator, something with units of joules minus something with units of joules will give me something with units of joules on top. And now I want to simplify this expression, which is what's going on over here. I'll walk you through it, don't worry. But I want to simplify this expression down. The way I'm going to do it is rewrite that numerator as joules over 1. And I'm going to write that joules per meter vertically, so it looks like that. And then I'm going to choose to multiply by the reciprocal of this fraction in the denominator so that we can get rid of all this stuff in the denominator. But if I multiply by the reciprocal, what am I trying to say? Let me back up. If I multiply the denominator by meters per joule, that reciprocal, I also need to multiply the numerator by that meters per joule reciprocal, so that overall I'm multiplying by a clever form of 1, and I'm keeping the value the same. Well, when I do that, I notice that I get joules and meters all canceling in the denominator. That's by design. And then in the numerator, I'm also seeing joules cancel. Those divide to 1. What I'm left with is just meters over 1, which is indeed a meter. So this quantity does have units of meters, and I can say, good job. We found the height of the loop. It's 10.2 meters. If we use the rough approximation that there's 3 feet in a meter, that's 30-ish feet tall. That seems reasonable for a roller coaster cart. And there we go. I did it. I found the height of the loop by using a general equation and isolating the find, and then finally plugging in numbers and evaluating and checking my units. Hope this has been helpful. Thank you for following along, and please let me know what questions you have.